This is problem 750 in Smith & Van Ness 8th edition. We've got liquid benzene at 25 degrees C and 1.2 bar is converted to vapor at 200 degrees C and 5 bar using a two-step steady flow process. The first step, we're going to compress by a pump to 5 bar. So that's just going to be going from liquid at 1.2 bar to liquid at 5 bar. And then we're going to follow that by vaporization in a counterflow heat exchanger. So the benzene is going to go into the pump at 25 degrees C, 1.2 bar. It's going to come out of the pump and go directly into a heat exchanger. In the heat exchanger, it's going to be vaporized and then heated even more. So we want to determine the power requirement of the pump and also how much heat, the duty of the heat exchanger. That means how much heat is transferred from our heat exchanger fluid, which is probably something like steam or maybe some other hot fuel oil or something. We're going to assume a pump efficiency of 70%, and we're going to treat the benzene vapor as an ideal gas with a constant heat capacity of 105 joules per mole Kelvin. So we've got some of our preliminary and given information here. Our T1, 298, 25 degrees C, 298 Kelvin. P1 is 1.2 bar, is coming out of the pump at 5 bar. And the first thing we're going to do in looking at this problem is realize that it's a two-step process. So let's not try to solve it all at once. Let's go through it one step at a time. So the first step is pumping of a liquid. And this is something that we've seen before. And I think that hopefully by now will be somewhat fairly straightforward for you to solve. So we've got a liquid. Inlet pressure is 1.2 bar. The outlet pressure is 5 bar. We need to know the required power for the pump. And so as we've done with problems similar to that, we've realized that there are several options for solving this kind of a problem. First option would be as if we had extensive benzene property tables. That would be really nice because then we could just look up. We know that the power required for the pump is just delta H. Work is equal to delta H. We could look up enthalpy values and calculate the delta H pretty easily. Unfortunately, we do not have benzene property tables in our textbook. They might be available somewhere, but here we're assuming that you have only the information in your textbook to solve the problem. The next option that you could use is we could use equation of state information. Go back to chapter 6. We did a lot of problems like this where we used equation of state and heat capacity to calculate delta H. But nothing is given in the problem statement. We're dealing with liquids here. So the last way that we could do this, or the next way we could do this, is we could assume that benzene is an incompressible liquid. And if you think about it, this is probably the best thing to do. Earlier we worked a problem with the water, and we saw that when you're pumping water and you're not doing huge pressure drops, that treating water as an incompressible fluid gave us the exact same answer to 3 or 4 decimal points as if we assumed that there was a isothermal compressibility in volume expansivity where that was used in the equation of state. So what we're going to do here is take the simplest approach, and that is assume that benzene is an incompressible liquid. So that is what is stated here. We're going to assume it's an incompressible liquid. We also found, if you remember the problem that we did with water where we were pumping water, subcooled water, we found that the temperature change for these small pressure drops is very, very small. And so we might be able to use that assumption later on as well. So we're going to assume it's incompressible for this first stage, pumping from 1.2 to 5 bar. To calculate the work, we're going to take the same approach that we did for pumping of the water. We know that the pump efficiency is 70%. If we had a 100% efficient pump, that pump would be operating in both a reversible and adiabatic process, or an isentropic process. And so with a lot of these pump problems, what we do is we assume isentropic operation. We calculate the delta H for the isentropic pump. And then the first law we apply for this hypothetical isentropic process, which says that the work for the isentropic process is equal to the delta H for the isentropic process. And then we apply our efficiency factor. Since work is being required, the real work is going to be the isentropic work, or the ideal work, divided by the efficiency. So the first thing we need to do is we need to figure out what is the delta H for an isentropic process for this benzene. And so we can use equation 6.9. Fundamental property relation, which applies to pure fluids, applies to pure benzene here. So that equation is dH is equal to TdS plus VdP. If it's isentropic, ds is equal to 0. So this term goes away, and we're left with dH is equal to V dP. We're assuming an incompressible fluid, so volume is constant. And so this is a very simple integration. Delta H for an isentropic process is equal to V times delta P. So that's pretty easy, pretty straightforward. The problem is we know what P2 and P1 are. We don't know what V is. How do we find V? Well, there's no information in the problem statement that lets us that just gives us the value of V. So what we're going to do is we're going to go back to chapter 3. If you remember, in chapter 3 we had some equations of state that worked for saturated liquids, and one of them was pretty complex, the corresponding states theory, and that required that we know volumes of a reference state, but we had the racket equation. Remember, we had some problems with the racket equation, and we can use that. Remember, the racket equation allowed us to solve for the saturated liquid volume. So this would be the saturated liquid volume. Is that going to be the same? Are we at saturation conditions when we're at our inlet condition or our outlet condition for the pump? No, we're not. We're not at we're a subcooled liquid in our pump. So how can we use an equation of state that gives us the volume for a saturated liquid? Well, the reason we can do that is because this liquid is incompressible. And so the volume that we calculate for a saturated liquid is going to be the same volume that we're going to have for a subcooled liquid. So there's not going to be any volume changes for an incompressible fluid with pressure or temperature. And so what we can do is go back to chapter 3 and use the racket equation. First thing we need to do that is look up all the critical constants that we have for benzene. And there are the critical constants. We then have the racket equation is equation 368 on page 112. If you're following along in your book, remember Tn is a normal boiling point for benzene in our table, in table B1. So this is at 1 atmosphere pressure, which is pretty close to 1 bar, and so which is pretty close to 1.2 bar, which is the inlet. And so we're going to use this Tn in the racket equation calculation. So we have to calculate a reference temperature, a reduced temperature. So that reduced temperature is going to be Tn divided by Tc. So our reduced temperature is 0.628. The racket equation is given here, where it's Vc times Ec raised to the 1 minus Tr, which is raised to the 0.2857. We plug that in and we get the saturated liquid volume of benzene at Tn, which is 353 Kelvin, is 96.807 centimeters cubed per mole. And what we're going to do then is we're going to assume that this saturated liquid volume is going to be constant throughout the entire pressure temperature regime that is going on in our pump. So this volume is staying constant in our pump. So now hopefully what you can see we can do is we can plug that volume into this equation for delta H for the isentropic operation, and we can calculate the delta H's, and we can calculate the work required for the pump. So delta H isentropic, 36.787 joules per mole. That's equal to the isentropic work. And then we take the isentropic work, divide it by the efficiency, and we get the power. We get the work that's required to do the real pumping. So that's 52.552 joules per mole. All right, so now we're done with the pump. Now we have to go to the second step, which is evaporating the benzene in this heat exchanger. And so if you don't remember heat exchanger, counterflow heat exchanger, what we've got is we've got usually counterflow is concentric tubes, so one tube inside of another. And we will have, so you have benzene flowing in the inner tube and steam flowing in the outer annulus tube. And so one is flowing in one direction, the other is flowing the other direction. That's what counterflow means. So we're going to evaporate the benzene. We got to think about what's going on in here. In previous work, we saw that the temperature change of a liquid during pumping changes very little. So that was our problem, I believe, was problem 744, where we were working on pumping of subcooled water. And we saw that the delta T was very, very small. So we're going to use that assumption. Since our pressure is not very big, we're going to use that assumption. We're going to say that the temperature at the pump outlet is the same as the inlet to that pump. And of course, that's going to be the temperature that's going into the heat exchanger. So T2, we're going to say T2 is equal to T1. This is across our pump, and that's 298 Kelvin. So what's going on inside the heat exchanger? Well, we've got three. We can think of the heat exchange, the heat being transferred to our benzene, in three different steps. The first step is where the benzene is heated from T2 to its boiling temperature. We're going to call that Tsat at a pressure of 5 bar. So the first step, we're heating benzene as a subcooled liquid at T2 in 5 bar to its boiling temperature, which we're going to call Tsat, and that's also going to be at 5 bar. We're then going to vaporize. So I've got this delta H of vaporization. We're going to vaporize, and that's going to occur at a constant temperature of Tsat. And then the third step is we're going to heat that saturated vapor to a superheated vapor at 200 degrees C. So this is a real critical part of this part of the problem here, is to realize that you have to calculate the heat for three different steps, the heat transfer for three different steps. The first step is heating the subcooled liquid to a saturated liquid. Second step is the vaporization at the saturation temperature. And the third step is heating the saturated vapor to a superheated vapor at 200 degrees C. For each of those steps, our first law is just Q is equal to delta H for that particular step. Because in heat exchangers, we have no work, no shaft work being done, and we neglect kinetic and potential energy changes. And we are also told, of course, that that is steady state. So what we can do then, again, we're going to divide and conquer. We're going to look at the first step. So the first step, we're heating at 5 bar. We're going from 298 Kelvin to the boiling temperature at 5 bar. So we know that the boiling temperature, we know the normal boiling point, which is at 1 atmosphere, or about 1.01 bar, is 353 Kelvin, or about 80 degrees C. But we don't know what the boiling point is when we're at 5 bar. And so we've got two options here. How do we find the boiling point at 5 bar? Well, if we had very extensive benzene property tables, we could use that, which we don't. Or our second option is we can use the Antoine equation that we had back in chapter 6. So that would be equation 690. And so our Antoine equation, bring that over here, is ln of Psat is equal to A minus B over Tsat plus C. And so here I'm going to call Psat is equal to P2, which is our 5 bar, which is 500 kilopascals. Right? We then go to the property table. I forget what the number is in the back of the book, and we look up these Antoine equation constants. One of the things that you have to worry about with the Antoine equation, especially if you're doing your calculations in MathCAD, is that you got to be careful with your units, and when you do the Antoine equation calculations in MathCAD, you could use units, but it's probably easier if you just don't use units for this part of the problem, because of course you can't take a log of a kilopascal or a log of a bar. So if you look at the units in the table, that is, this is in table B2, I believe. You'll see that the Tsat has to be in degrees Celsius, and that Psat has to be in kilopascals. That's the only way that these constants will work. So these are dimensionless, and you plug that in. So I've set Psat equal to P2, which is 500 kilopascals or 5 bar. Right? So that's our temperature, or that's our pressure. What we need to solve for is we need to solve for the temperature, Tsat at 5 bar. And so I set that equal to just 500, make it dimensionless, so that MathCAD doesn't think there's something wrong with the units. And then I just tell MathCAD to solve for Tsat. It solves for Tsat. It's a little verbose here. You could probably simplify this a little more. We get a dimensionless answer for Tsat, and that is in degrees C. And so all I've done here is convert it to Kelvin, and I get my Tsat, this is my boiling point at 5 bar, is equal to 415.92 degrees Kelvin. Now, one of the things I noticed when I was doing this problem, this temperature here, this Tsat, is higher than the temperature range that's given in table B2 for the Antoine equation constants being valid. So theoretically, we're out of range, we're out of spec. So what do? Well, for the purpose of this class, I mean, we could try and go find another table and some constants, or we could just go with what we've got and realize this is the only source we have if we confine ourselves to the universe of Chemie 223 in the Smith and Van Ness 8th edition textbook. So that's what we're going to do here, is we're just going to kind of ignore, I believe the max temperature that these Antoine equation constants were valid for was something like 104 degrees C. We got 142. We're going to ignore that and assume that the Antoine equation is still valid at these conditions. Now, if I were doing this for my job, I would certainly go out and find something, find some additional resources to figure out a better estimation of the boiling temperature at 5 bar. But as I said, for the purpose of this class, using the information in your textbook is good enough. So now we know what the saturation temperature is, what the boiling temperature is at 5 bar. So what we have to do then is we have to calculate the delta H, the heat required to raise our temperature from 298 K to 415.9 K. All right, so we need to find the heat capacity because Q is going to equal delta H, which is going to equal to CP, the integral of CP dt. So when we do this part of the problem, we got to realize that that's kind of a big temperature change. We're going, that's over 100 degrees C. And we were not told anything about the liquid heat capacity. Remember, the problem statement gave us some information about a heat capacity, but that was for the vapor, right? This is not the heat capacity of liquid benzene. This is a heat capacity of benzene in the gaseous state and as an ideal gas. So what we're going to have to do is we're going to have to use an average heat capacity and use the polynomial form of Cp as a function of T, like we've done for other problems. And so we go to table C3, because remember this is a liquid. We're dealing with a liquid, and table C3 has the values for liquids. And so we look up the values for your heat capacity polynomial constants, so A, B, and C. And again, remember to get your exponents correct and get your units correct so that MathCAD figures everything out. Again, when I do this, I always want to do a little double check, triple check to make sure I did everything right. And so I just set, okay, this is 298K. I plug this in and I see if I match the value that's in the table. It's a free check. So I know that I haven't made some sort of error in this calculation. So now I just do the integration. And here again we can integrate by hand and plug this. This is pretty easy to integrate. This would be AT plus BT squared over 2 plus CT cubed over 3, or we could just let MathCAD do it. And remember, this is CP over R is equal to this term, and so we have to multiply through this. This whole thing has units of temperature, so we multiply through by R, and we get a delta H of our first heating step is equal to 18.268 kilojoules per mole. Now remember, this is the enthalpy change for the first heating regime, which is going from the pump outlet, a subcooled liquid at 5 bar, to the boiling point of the liquid at 5 bar. So that's our first heating step. So now we're at the boiling temperature at 5 bar, and our next heating step is going to be delta H of vaporization. So we know that phase change occurs at constant temperature. For boiling, we need to know the delta H of vaporization, but we need to know it at a pressure of 5 bar. If you look up the values in the tables, they give that, and again I forget exactly which, it's table B2, they give the delta H of vaporization at 1 atmosphere at the normal boiling temperature, and that's pretty close to 1 bar. But we're at 5 bar. So how do we find the delta H of vaporization at 5 bar and our Tsat of about 415.9 degrees K? Well, this is where we go back to chapter 4, which we kind of skipped in the lecture, and we're just coming back and picking up some things as we go along that are in chapter 4. If you look on page 143, I believe it was a guy named Watson came up with this method back in 1943 to solve for delta H of vaporization if we knew the delta H of vaporization at another temperature. So if we know, so delta H1 is the known delta H of vaporization at temperature 1. Delta H2 is the unknown delta H of vaporization at a different temperature, T2. And so this equation is given to us. It's equation 414 on page 143. Delta H1 is a vaporization temperature at the normal boiling point, And so that is going to be, if we look that up in our table, that is 30.72 kilojoules per mole. Our TR1, this is the normal boiling point temperature divided by the critical temperature. So we already tabulated the critical temperature up above, and so TR1 is 0.628. TR2, this is our new temperature that we want to find the delta H for, delta H of vaporization. So we've called that, in this problem, we've called that Tsat. So this is the 479, or sorry, the 415.92. This is a boiling point at 5 bar. So TR2 is 0.74. We solve this equation for delta H2. So delta H2, this is delta H of vaporization at the 415.92 degrees K and 5 bar. That's equal to 26.825 kilojoules per mole. So now we have the second part of our heat duty calculated. The third part is going from our saturated vapor to superheated vapor. So after this step, we're at saturated vapor. Now we go to superheated vapor. The superheated vapor is going to be at 5 bar and 473.15 Kelvin. And so this is an easy problem for us now because the problem statement said that we could assume benzene is an ideal gas at these conditions. So, and it also has a constant heat capacity, so we don't have to deal with that infernal polynomial form of the heat capacity. So our Tsat is our initial temperature, our T3 is 473, our final temperature. Delta H is just Cp dt, Cp delta T, and so that's about 6,000 joules per mole. To calculate the total amount of heat transfer in our heat exchanger, we then just sum up all those delta H's, delta H1, delta H2, delta H3, and we get a value of 63.554 kilojoules per mole. So this includes heating a subcooled liquid to saturated liquid, vaporization of saturated liquid to saturated vapor, and then heating of saturated vapor to superheated vapor. So summary, you know, there weren't a whole lot of new things in this process. Most of these things you've probably been exposed to at one time or another. We haven't done a lot of phase change calculations, but this is something that you should have picked up in your previous courses. Just remember that whenever you do a phase change, liquid to vapor, vapor to liquid, solid to liquid, liquid to solid, remember those phase changes always occur at constant temperature. And so once you remember that, once you realize that, it becomes pretty easy. The only thing that we really didn't cover in any of the lectures or any of the problems was this information in that Watson equation that gave us, it was an empirical relation that tells you how to calculate delta H of vaporization at another temperature. And that's just something that I wanted to bring up in this problem so that you know that it exists and you can use that. Other than that, I mean, the work calculation for the pump, that's something we've seen before, and something that you could have should have been able to do pretty easily. Here in this problem, we didn't have to mess with any equations of state. We didn't have to do any residual calculations or anything like that. Didn't have to look up a whole bunch of stuff in the steam in property tables and do a whole bunch of interpolations. It was fairly simple. We assumed that the fluid was incompressible. All right. The only equation of state we really had to deal with was a Racket equation, which is for a saturated liquid. And since it's constant volume, the saturated liquid volume is equal to the subcooled liquid volume. We then did the isentropic work calculation, and we used the efficiency to calculate the real work. We also used the assumption that the pumping process with a moderate change in pressure is going to have very little effect on the temperature of subcooled liquids. So that let us say that T2 is equal to T1. And then just to reiterate yet once again, I realize I'm repeating myself, but I think it's very important that you understand what's going on in this heat exchanger. Is we heat the subcooled liquid to the saturation temperature. So it's a saturated liquid. We then go from saturated liquid to saturated vapor at that Tsat. That's our delta H of vaporization. And then we do the heating of the saturated vapor to superheated vapor. And the problem was made easy in this case by saying that it was an ideal gas with constant heat capacity.